So, I slightly updated lecture note, slightly. I'm not sure if I can go today the amplitude, but amplitude section is poorly written. So, but my schedule is very occupied and crazy, so I didn't have time to fix this issue. So maybe next week I will improve the section 6. Unfortunately, I mean current situation 6 is very unfortunate, but I know, but I will correct later. Where's the choke? And also last time I didn't explain BC goals properly so much, so I will tell you. So the homework is there, so you can pick it up. So the homework over there. So you should pick up now. I mean, if you have submitted, and I will tell you. So the Fermat, let's see. That's strange. That's better. Okay, so I graded Fermat, free Fermat, which is very important, but most of them didn't do correctly the OPE. I mean, either just copy and paste from book, or they just didn't do properly. So let's see. I posted solution 3. You can take a look at it, but anyway, but let me explain how. I'm not sure. So this week I asked you to do OPE for BC Ghost. I'm not sure you guys did properly, because if you cannot do Fermat, free Fermat, it's the same for free bosons, unfortunately. So okay, so free Fermat, so the action is given by what was 1/4 pi dz square and psi d slash psi. And this is the action, psi bar, I would say, psi bar. And then you can use just a free. So let's say gamma 0 is equal to 1, 1. Gamma 1 is equal to I minus I. And this can be written in terms of 2 pi d squared z. And some people didn't use the proper normalization. So it's 1/2 I1. So this is the convention. So this is 1/2 pi you have to get. And then the stress energy tensor, this one is 0, but this one is 1/psi, and I call it T of z, and z bar minus 1/2. This can be easily obtained by just taking for the proper normalization. As first, remember H minus and TAB. You can do the variation with respect to metric. Yeah. 4 pi. So you can start with the. You can just change the metric, introduce square root h here, and here you have also g appear here. That's one way to derive And another way to derive is TAB and also minus 2 pi. Lagrangian, if you use flat case, maybe A, B phi minus HAB. I mean, this one is already written in the lecture note, minus 2 pi, but people didn't use script normalization. I don't know why. And you get this one. And then from equation motion, it's easy to derive psi z psi w is equal to 1 over z minus w. This is okay. This is from equation motion, it's easy to derive. And so I just ask you to derive this OPE. So let's do step by step. I don't know. I mean, you should write what you did in the homework properly. So one way to take this one. So this one is equal to minus so one way to do this is, I mean, you need to bring psi into here. So since psi is under commute, you get another minus sign. Okay. So therefore, what you get is the 1 over z minus w, but plus sign. Okay. So since you bring psi into here when you take the weak construction, so you get the minus times minus plus. Another way to get the contraction, you should specify what you did in the homework. It's very hard to, and some people did clearly cheating. And also psi z, so minus 2 z minus w. Okay, and then since there is homomorphic derivative, you just act on homomorphic derivative. Okay, so that's what you're going to do. So this is W. Sorry, W. I think I'm wrong. Sorry. So this is Z, and then you just take the homomorphic derivative with circuit Z, so you get the square and the plus. Okay. Okay. That's what you get. Do you understand? Do you understand? Do you guys understand? I mean, if you cannot this computation, I mean, you. What? First time plus. So if you take psi into here, you should come early if you want to. If you bring this one to here, you get the minus sign due to Fermion anti-commutation relation. And you get the plus sign. So, okay. Then take the Taylor expansion with respect to z around the w. So you get the 1/2 partial w z minus w. Maybe I should use this one, bring it to here, plus I mean, it's people. I mean, if you cannot this computation, you won't understand string theory at all. So therefore, the psi is the conformate, h is equal to 1/2, and then it's primary. People just use, even though people just use different notation for TZ, like as people start with 1/4 by using this OPE, 1/4 in front of here. Somehow people get this answer by copy and paste the solution. That's not good. I mean, you just use properly what you did for which operator you take a contraction and so on. Otherwise, it's hard to understand. So T of Z, T of W. Next problem. Now, unfortunately, among people submit is only one how has done correctly. I know the Jiang Hao can do that, and also Zhen Dong can do it. What's his name? He's not here. He's not here. Fan Dong. Yeah. Shandong. Jin Shandong. Right? Shandong. Yeah. So let's see. So this one is 1/4 Shandong. Yeah. Let me just. If you want to learn string theory, you should do this kind of computation properly. So the leading term is what? So let's do this. So let's see. But first, let's take the contraction like this way, and the contraction like this way. Okay. Let's do contraction like this way, and then what you get is the. So let's see. First, you need to bring it to here. Bring this one into here. You get the minus sign. So minus 1/Z minus W 1/4, and then you should do the contraction between them. So therefore, what you get is Z minus W of Z, partial Z and partial W. Okay. I'm doing, and hopefully you understand what I'm doing. And then what you get is this one will give you square, and this one will give you minus cube, but a minus 2. Okay, do you understand? And then the next thing what we can do is the so next we are going to take this contraction and this contraction. Okay. Then so we don't need to take minus sign. So once you take this one, what you get is the plus minus 1 Z minus W square, and here what you get is 1/Z minus W square. Okay, do you understand? And the next, I'm going to take only two of them. I mean, I'm doing for you guys, right? Please follow. So I don't want to be honest. I wish you guys can do that by yourself. Then, so you need a minus sign because you just bring this one to here. You get the minus 1 Z minus W, and then what you have is denominator psi Z and psi. Okay. And also, so next, and so next, I think. So let me bring this one into the following form. So this one should be equal to yeah. So yeah, sorry. So once you take do the Taylor expansion with respect to Z in terms of W, I mean the singular term only show up this way. The next derivative will give you Z minus W that cancels with denominator, so it's no longer singular. So therefore it's okay. And the next we are going to take. You should in the homework you should also tell which one you take a contraction. So you just take this contraction. I mean, once you bring here and bring here, you get the two minus sign, so therefore it's okay to take plus sign. But here you have a square and then psi z and psi w. Okay, so this is how you get. So then you need to do the Taylor expansion. If you do the Taylor expansion, what you get is this is w. Okay, but however, you have subleading order is z minus w. I hope I'm doing correctly. If I make a mistake, just tell me. And also, you have to take square psi w and then psi. Okay? So that's then. If you do the Taylor expansion, and next, I'm going to do the following. Did I do this one? No, not yet. So this one. Then what you would get is again psi z partial psi w and then z minus w squared, but you get the minus sign. Okay. Therefore, if you do the Taylor expansion, it becomes w and minus partial psi w. That's what you get by the Taylor expansion. So next, you're going to do the following. So then you get that. If you bring it to here, you get the minus sign, and then so just first let's do this derivative, and you get the square and another z acts on here, you get the minus 2 and the cube. So therefore this is plus, and what's left is psi and the psi. Okay? So therefore you have 2 psi z, psi w. Okay? And we do the Taylor expansion. So this is first term. Another term is the 2 psi z minus w square, and also what you obtain is the second derivative, but there is a 2 factorial shop. So z minus w psi Okay, so this is how you do the OP. Okay. And then you just summarize everything. If you summarize everything, 1/4, and this is the most singular term is these two, and this is 2 minus 1 is equal to 1. So therefore, it's z minus w 4 to the 4th 1. Okay. This is how you get the central charge, and the next term should be z minus w square. You should collect everything z minus w square. Okay, so then z minus w square term is this guy and this guy and this guy. Okay, and what else? This guy and this guy and this guy, right? And if you collect, this is 3 minus this one. Am I doing wrong thing? Seems like I make a mistake. Did I? Oh, I think I understand what I'm doing, where I made a mistake. Sorry. I think everything should be minus. Because, I mean, everything minus. Do I understand do you understand correctly? So if you swap them together, you get the minus sign. Okay? So since I swap, so if I take derivative on this one and swap, I should get the minus sign. Okay? And also, So if I take second derivative and swap, I should get the minus sign. Okay? It's the same. So this is plus, but if you swap them, you get the minus sign. And at the end of the day, you have a full term. Therefore, 4 times psi pressure psi W. Okay. And then next, cube term should cancel. This cube should cancel with somewhere. Oh yeah, since this psi and psi are harmonic, if you anti-commute, it's get the minus sign. It should be 0. Okay. Okay. And then just collect this 1 over zeta. This should be equal to what? So yeah, so 2 times psi and a minus sign, I think. Everything minus sign, okay? So this is a collection. Okay, everything. Since I take here, I take derivative and I just swap, I should get the minus sign here. Sorry. Okay, so this is the result. So that at the end of the day, so what we get is 1 over 4 z minus w to the 4th plus 2 times t. Oh, this should be minus, sorry. This should be minus of w z minus w squared plus portion t w z minus w. Okay, that's how you obtain. So this is how you obtain. So you should tell each step why you get the minus sign and so on. I also did some mistake, but eventually you should get this result. So you should explain one by one. Okay, hopefully you understand. I already explained how to do the OPE for Fermat. And you should do the same thing for BC Ghost. I hope you guys do that. If you think you haven't done correctly, you should submit from now. You should redo it and submit from now. Any question about this OPE of psi? Okay. Okay, so let's. I think it's very tedious. It should be very tedious. For BC Ghost OPE. Okay. Let's move on to the. So BC Ghost. Okay, so last time I was a bit in hurry about talking about BC Ghost. So let's do a bit review a little bit of BC Ghost. So so what we are talking about is that so we want to fix the gauge. So for so if you do the path integral, the HAB. The x and the e to the minus h sigma model. So this is path integral. So there is a Weyl symmetry and also diffeomorphism. And diffeomorphism. Okay, so then, so we want to fix the gauge in such a way that the what inserting determinant of the inserting this one dxc delta h minus hc and determinant of delta h hat C delta H. Okay. So that's we want to insert in the path integral. So moreover, so essentially, we want to fix some metric. So H theta is the ambiguity for e to the omega and also 2 omega. And then there's a ambiguity for metric, so we want to fix some metric by inserting this one. And then to insert, so this, I call it, I think, Faddeev-Popov determinant. This Faddeev-Popov of H theta. To insert this one, I just use the fact that the delta H AB in infinitesimal version of this one is indeed 2 omega tilde H AB plus P dot E AB. So where P is the so-called conformal killing vector, so this AB so in fact, so when you, so this is the generator of conformal transformation. So therefore, if this is 0, if P E is equal to 0, so this is epsilon is called conformal killing vector. Okay. And it turns out that this Faddeev-Popov determinant is determinant of this operator P. Okay? And therefore, to insert this Faddeev-Popov determinant, we insert we introduce so-called ghost field to determine the to compute determinant. So the ghost field is 1 over 2 pi is equal to the square sigma square root H hat BAB P dot CAB. And note that I missed the point that the last time. So this one is indeed, as you can easily see, this is symmetric and traceless. Symmetric and traceless. So therefore, BAB, we take also the, therefore we take this is symmetric and traceless. And if you compute this one, honestly, this is equal to 1 over 2 pi d squared sigma square root minus H. Oh gosh, okay. I think I just already take the Euclidean signature. So BAB delta. And then if you take the conformal gauge, so ds square is equal to e to the 2 omega dz and dz bar. So dz bar, so this action will become 1 over 2 pi d square c dzt b cz bar. So that's how we obtain the ghost action. And from there, it was a bit sloppy and 2 paths again. So then we call it BZZ. equal to B, and then CZ is equal to C, and then I'm going to focus on homomorphic part. So then, so equilibrium motion tells us that at the B and C are holomorphic field. And then, so what we have done is that indeed CZ and BW, indeed, also I should mention these are fermionic ghost. And in homework you did even bosonic ghost for beta gamma system. These are very important to the CFT. And then the OPE of them are given by, so OPE is given by T minus W. And then if you swap them, you get the second solution. And then I missed that of course it's a holomorphic fermionic quantity. This is 0, and also CC and CW is also 0. And then from the since this is the low indices of holomorphic quadratic differential, it's a conformal dimension 2, and you can easily also derive by using taking OPE. So therefore, what I meant is the T ghost C this is homework you have to do. This was homework. And then, so this one you just take the action derivative of T HAB, and then 4 pi over square root h and minus I think. So they just start from this action. And take the variation with symmetric, you get this one. And take conformal gauge. Then T ghost of C, CW is equal to minus CW Z minus W squared plus, and then T ghost C BW, this is 2 times BW Z minus W squared plus. Okay, so that's how you obtain the OPE by using this one. So this one is very easy. So if you take C contraction with this B, and C contraction with B here, you get the minus sign here, and the square. And this coming from C with this one. C with this one will give you this one. Okay. The same thing happen. B with this guy will give you this one, and B with this guy will give you this one. Okay. So therefore, C and B are primary, and conformal dimension of C is minus 1, conformal dimension is equal to B is plus 1. That's consistent with this quadratic differential, and then the upper script vector. Okay. And you did OPE for TT, which is very tedious. TT is indeed, TT ghost is indeed minus 13, Z minus W, so this is homework, 2T, Z minus W square. So therefore ghost field central charge is equal to minus 26. So to banish, to have the 0, 1 anomaly, the target space of the boson should be 26, sorry. Dimension has to be 26. That's what we have done. Okay, so then I did a very poor job in the BRC quantization. So let's review what the BRC quantization is. So since we introduced Gauss field, the Hilbert space is not only the boson, but also you have the Gauss field. So we have to specify what kind of condition you need to impose to give Gauss degrees of freedom. So 1 over 2 pi d squared c, and then I just correctly reproduce. So this is the total action we are going to consider, and this action has the BRC symmetry, so which is the so I'm going to focus on only homomorphic part. Oh, sorry, X missing. Yeah, I think for BRC symmetry I need to include both. Oh, sorry. Thank you very much. Oh, now I understand what I'm doing. Sorry. So x mu, yeah, this is what I. Thank you very much for pointing me. There's a lot of mistake I did, so please point out. And anti-homomorphic part is the same. Just put the bar, okay? Okay, and then so this is the action is invariant. Okay, so this is Beer transformation. It's very transformation. So it's very tedious, but the action with this Beer transformation is x plus s ghost is equal to 0, so therefore we can have method current. Okay. And the explicit form of JB can be written there. So this is also tedious exercise to find the explicit form, but it's kind of, I mean, it's possible to guess the form. Coming from this one. So JB is C of Z, so it's tedious, but you can kind of guess the form. Ghost and Z 3 over 2 okay, so and then one can plug in explicit form of T ghost and T, and then yeah, BSC charge can be understood as the spatial derivative, no, spatial integral 2 pi d can be 2 pi I. Okay, and then yeah. And then I think you computed this JB OPE as far as I remember, or JB OPE. Yeah. So he just computed JB OPE. So this is a part I missed last time. But if you compute this JB Z and the JB WOPE. So the answer is written in the homework. So it's equal to minus cx minus 18 z minus w is a cube. I already forgot. The cube c w, and also you have the similar term. So cx minus 18 or c minus w, c, is it second derivative? Yeah, derivative, and then c x of minus 26 over z minus w is equal to c partial cube c, as far as I remember. Yeah, and the 12. So BRC, BRC charge means that as I mentioned, so the important thing is nilpotency. So to impose BRC quantization, you need to have this condition. Okay, you need to have this condition. So to have this condition, you have to integrate over again. So just do the QB square can be obtained by dz 2 pi I and the dw 2 pi I. Sorry, 2 pi I and jb and jbz and jbw. Okay? That's what you need to do. And this one, so this one is equal to 0. This one is equal to 0 only when this one vanishes. Cx is equal to 26. Okay? Only equal to 0 when 26. So therefore, this BRC symmetry becomes nilpotent only when the target dimension 26. So there are a bunch of ways, numerous ways to derive the target, this critical dimension of the bosonic. Okay, so that I missed last time. So I was in rush last time. So hopefully you did. This is also very tedious once you did the homework. So I'm not sure you guys did that correctly, but I told you how to do the OPE for Fermat. So if you think you haven't done correctly, you can submit from now, and you can do it for in the weekend. Okay, so that's. Okay, so once you have QB square is equal to 0, so we can impose that the physical state is impose a condition for physical states in the sense of the Faraday-Popov. So this has to be QB cohomology. So this is QB exact. So the QB close divided by QB exact, roughly speaking. Okay. So, and then, one can do the mode expansion for QB. So it's important to have mode expansion for QB. So, which is, it's also tedious, but one has to do if you try to understand the BRC quantization. I don't know, to be honest, who did this tedious computation first. So M and N, and where Z is given by BM Z minus M minus 2, as far as I remember. And CZ is equal to sum of Cm Z minus M plus 1. Okay. That's the model expansion one can write down. Okay, so that's the model expansion. And then let's impose this physical condition. Okay, so then, so the bosonic state, so this x mu, again, is just have the model expansion alpha mu. What was that? N c to the minus n. Is it correct? Yeah, I mean, as far as I remember, this should be minus 1. Okay. So this has a model expansion like this way. So yeah. So model expansion x mu involve log z and log c, and also zero mode is momentum and also center of mass motion. But I prefer this one because it's more primary. I mean, some people call it x mu is primary of conformal dimension 0, but some people doesn't treat primary. I don't know. Anyway, so this is easier too. And then so physical state is again. So n physical state is equal to 0 when n is greater than 0. Okay? So this is the condition we impose. So this one is already fixed. However, and the vacuum is so the Fock, you can just create a Fock space by using active and negative mode. So you can act bunch of the Fock space, a bunch of the negative mode to create a Fock space, a bunch of. You understand what I mean? U1, UK. So this create a Hilbert space of the bosonic mode. However, the question is, so this is vacuum with momentum K. So now we have a sector for ghost. I already erased that, so the ghost here. And the ghost for fermionic, so we have indeed, so we need to consider the two spin up and down system. So we need to consider spin up and down system. And the question is, it's BC and the fermionic, so we need to consider spin up. The question is, which one is vacuum? Question is which one, which should we take as a vacuum? Yeah. So this is the question we can ask. So of course, we impose a similar condition of this one. So once you act the negative positive mode on this the two spin up and down system, sorry, last time I just make you confused, I guess. N greater than 0. Okay, so even both spin up and down. When for both on spin up down state, once you act this annihilation operator, n greater than 0 is called annihilation operator, they are annihilated by positive mode, and the negative mode. The question is, a negative mode will create Fock space for Fermat. Okay. Okay. So. And the side of the issue, a sharp Fermat, so zero mode is coming from here. is the, of course, experiment, so it should satisfy this condition, but we can just show this one is equal to indeed 1. Okay. So that coming from, that can be shown by using BC. So if you use this one is equal to plus minus, I already forgot which one is correct, by using this one and do the model expansion. So one can obtain this one. I already forgot the plus minus. So you should correct rewrite in a note if you want. This come from here, so it's a good exercise to do that. I just don't want to do that. I mean, yeah. So if you do homework this week, you understand how tedious tedious computation you have to do when you do the string theory. Okay. So the question is, which one we should take as a vacuum is that so we impose the condition is B0. Impose the condition B0 physical state equal to 0. So this is called the big H. So once you impose this condition, so let's see whether we can use this condition. So B0 equal to 0, C0, sorry. Okay, let's see why you get this one, this condition. Let's create the, what should I do to check why you get this condition? So, okay, so, I mean, since B0, okay, now I understand what's going on. So, okay, so if you pick the vacuum, so maybe it's a choice of vacuum, how to get the, let me see. So since this is, it's easy to see the consistency condition. So if you do this one, this should be 0. Since B0 squared is equal to 0, so this should be 0, and this B0 acts on the spin down state, you get 0. Okay, that's the consistency condition. You can do the same thing for C0 squared negative is equal to C0 up spin. You get this one, and the question is this one. Okay, let's do step by step. So B0, C0 plus C0, B0, this is 1. And let's ax this one into here. Okay, let's ax this one. Then, since B0 analyzes this one, and so therefore you just act the C0 on down one, you get the up spin, and the B0 acts on up spin, you get the negative. So therefore this is equal to, so this one you can ignore because B0 acts on negative spin, and down spin we get 0. So therefore what you get is this one and this one. At the end of the day, down, and if you act on C naught, you get up, and if you act on B naught, you get down. So you get this is equal to 1. This consistency condition is okay. And you can do the same exercise for up spin. So now, this is equal to C naught, B naught. Okay. So it's a choice, actually. It's a choice. And then now I think C naught acts on up spin is equal to 0, so you can ignore this part. And but again, you just have up, down, up, and at the end of the day, you get the this one is equal to this one. Okay. So it's a consistency condition. And then here, so this choice can be made. Once you pick the down state as a vacuum. Down spin is vacuum. So since this down spin is annihilated by B naught, so it satisfies the equal condition. On the other hand, B naught acting up spin is no longer 0. So therefore, this is not the physical condition. This is a choice. Okay, this is a choice. And if you want to pick down spin as a vacuum, this commutation relation tells you all the other relations. That's what it means. Okay, this is a choice. Okay, so this is a choice we made by using these two conditions. So therefore, now we pick the vacuum. So the Fock space created by this gauge field is just given by just Bn, and also Cn acts on this downspin state where n is the creation operator. So these are Fock space you will get. B and C act on this vacuum. That's a Fock space coming from gauge field. However, one has to be careful about C naught. Since C naught acts on a down state, we'll get down spin will give you up spin. Okay. Therefore, up spin is not annihilated by B naught. So therefore, C naught cannot act on the down spin. Okay. If you act it, you get some unphysical state. Okay. You get the unphysical state up spin. Okay, so the reason why you get this two spin system really coming from this factor. So to get this commutation relation correctly by sandwiching by states, you need to have an up and down spin state, and we need to pick some state for vacuum, and we impose some condition for physical states. Okay, so those are Fock state, and what is a Fock space, and what is the so physical state? It has to be annihilated by QB0 when D equal 26. Okay, D equal 26, you have an important or already erased important condition QB square equal to 0. Okay. So therefore, this is the Faddeev-Popov BRC quantization condition. Okay, let's look at the step by step about. So I don't. Okay, good. I keep this one. So then let's look at whether it satisfies the condition QB. K 0K. So 0K. And then 0K and then down. So this is a vacuum. So it should it's a physical state. It should be annihilated by the the BRC charge. And let's look at how this one acts on this guy. And it turns out that the so this is normal ordering. Usually normal ordering we just bring creations operate to the left and annihilation to the right. So usually it's this normal ordering will annihilate the state in the vacuum. So what's relevant is this part, and moreover, it's a zero mode is the relevant part. Okay, L 0x. Yeah. So if you consider, so you can also look at the zero mode, 0, 0, 0, but here it becomes numerator is 0. So therefore, there no zero mode will show up here. So what's relevant is this zero mode here. 1, and then 0k. So since this is bosonic state, and C and the bosonic states commute, and the bosonic is the x, so therefore C and the x will commute, so that you can bring to the right, and this is equal to L naught x minus 1, and then Lux acts on 0k and upstream states. Okay, so C naught acts on down state. You just follow this rule. So therefore, one has to impose the conditions that the only when you act L naught on X, you have you get the L naught X acts on this one is the vacuum. Okay, it's just the vacuum itself. Okay? And if you look at the L naught, the explicit expression L naught X, which has the form like this way. And then, so since this one is also written in terms of everything normal ordering, all the creation operator goes left, and the annihilation operator goes right in this dotted part. So therefore, this part is just annihilate the vacuum. Okay. So however, this part is important. So if you act this one onto here, what you get is the alpha prime p square is equal to m square, I guess, minus m square. P square is equal to minus 1. This is the condition you get. Okay. So therefore, from here, what you get m square is equal to minus 1 over alpha prime. Okay. And this is the condition for tachyon. So again, the mass is negative. It's for tachyon. Okay, so that's the condition you get. Okay, let me move on. So So let's first consider, so this is tachyon, okay? So the next thing we need to consider the first excited state. What are the first excited states? Okay. So first excited states, of course, can be obtained by acting on this one, or B minus 1 and the C minus 1, right? Okay, so I think I should put the mu here, and the mu and the mu, okay, something like this way. So therefore, what we can have is something like a psi, which is, so this is open string state actually. So only how to say, left holomorphic sector should act on. Not, I already forgot the tilde part. So anti-holomorphic part I already forgot. Okay, and just only focus on holomorphic part. That can be done for open string sector. So if you do a homework, you can just identify holomorphic and anti-holomorphic sector by using a boundary condition for open string. So then you just act this one. You can act. This is first excited state, and from here you can have this dot means you just contract like mu, right? Therefore, 26 state. This is 28. One state and one state. So there is in total 28 parameters show up. But some of them should be killed by imposing this BRC quantization condition because it's too much. Okay. So at the end of the day, how many physical degrees of freedom for you should have for open string? At the end of the day, how many?
26.
No. Good. So it's a first exercise is massless. That we know. Okay. Therefore, it's if you take light cone gauge, so only physical states in transversal direction. Okay. So it should be SO24. It's a representation of SO24. Little group. So we should kill 4 parameter by using BRC condition. That's what we are going to do. Okay. So first of all, we can do the following things. So let me. So by using first of all, one can do the following things. So let's see. So B0 anti-commutes with B minus 1. This is anti-commute. Anti-commute. Okay. Anti-commute. So therefore, and also anti-commute with commute with this one and anti-commute with this one. Okay. B0 and C minus 1 is equal to 0. So therefore, so B0 acts on psi is essentially this part up to sine, this part up to sine. I think minus, it becomes minus in this case. Minus the same piece will show up in here. And then C B naught, okay, this one. So therefore this is equal to 0, okay? This is equal to 0. So B naught acts on physical state should be 0, okay? And then what we are going to do is just using just commutation relation. Just commutation relation. That's why you need to do OP computation for the model expansion. Okay, so good. So last time I was too quick and also my brain's too occupied. So was too occupied. So today is a bit. I did slowly. So we use the following computation relation. So if you use JB Z, so you can just use OPE form. You can compute this OPE. Okay, OPE. From here, one can deduce that the essentially this will give you the following. So this OPE should give rise to the following. So delta V, which is IE Tx plus T ghost. Okay. Did I ask you to compute this one in the homework? I already forgot. Maybe not. But essentially you need to do this one in the homework. But anyway, so you can do the thing. So from here, definitely leading term should be something like the most, how to say, most less singular. Okay, do you understand? Sorry, least singular term. One of the term. Oh, sorry, no, I should say one of the terms should be this one. This one should be something like this one. Should be. Okay. That's you can easily see right from here. So then, if you take the zero mode, so the mode expansion for this one, so what you do is QB and B naught. Should be, you just get the zero mode. So you should get this one from here. Yep. So by using this one, so one can deduce that the QB, so for physical state, we know that the QB and the B naught should act on QB, B naught plus B naught QB acts on, I should act physical state psi. Physical state psi. So these physical states are analyzed by QB and the B naught analyzed by psi, so therefore this should be equal to 0. Am I making a mistake around here? Did I make a mistake?
Is the definition of
L ghost. Oh, thank you very much. So, okay, I'm going to give you. Okay. L ghost is, so T ghost of Z is spanned by L ghost n Z minus n minus 2, okay? And also T ghost, we know that the T ghost should be written minus 2 B partial C plus C partial B. I already forgot. Which is this opposite? Huh? Is it correct? Yeah, correct. And then if you use this expression, one can give you the explicit expression for ln ghost. When I was a student, I did the BRC ghost computation. It takes huge time to do all the computation. There's a typo in my lecture note. And again, you just need to take a look at so this is equal to 0. So just plug this one into here. Okay. So just plug. So we know that the physical state should satisfy this condition. Acts on physical state has to be satisfy this condition. And we know that the L0, I hope I don't, okay, L0 is written here. And also L0 ghost is written B minus 1, C1, C minus 1, B1 plus dot dot dot. So if you use this one, you just plug in 0 here. And the relevant part is the 1. Relevant part is 1 here, n is equal to 1, and m equal to. Why did we include? Just a moment. Again, it seems like I made a mistake, or not. It seems like I made a mistake. There should be plus 1. Minus 1 term should show up. But why this is not correct? Just a moment. So I'm taking m equal to 0. This should be minus. And n, so let's do honestly. So this should be m equal to 0. So therefore, what's remember minus 1, b1, c minus 1. Okay. And then if you take n equal to minus 1, it should be plus b minus 1 and c 1. And this is honest computation. And it seems like I missed this part. N has to be 0, so therefore it should be 1. Then it should be 1, minus 1, sorry. Plus, then I got confused. Why then?
Because you use anti-computation of B1 minus 1 is 1.
Oh, good, wonderful. Thank you very much. Good. So thank you very much. So I just do the anti-computational relation. So thank you very much. Plus minus 1. So let's do honest computation. So L0 is equal to minus 1 plus this one plus dot dot dot. And this one should be equal to 1 plus no. This one should be equal to minus c minus 1 plus times b1 plus 1. Okay. So therefore, the commutator of anti-commutator of b1 and c minus 1 should be equal to minus 1. Okay. Do you understand? Is it okay? And this 1 should cancel with this one. Okay. And then what you end up with is this one. Sorry, thank you very much. Okay, good. So then we are going to what we are going to do is that the plug this one and this one into here, and what you get is what? I should get the k-square equal to 0 condition. So what I would get is psi L naught x plus L naught ghost minus 2 psi equal to 0. Let's see, let's do step by step. Alpha p squared coming from here. And then now it's first excited states. It should see, right? It should see something. First excited states, so therefore, so what we have seen is something like a vacuum alpha minus alpha 1, alpha minus, and 1, and psi vacuum. Okay, so this is the one we will see, and also another one we will see is the so it's very tedious computation. Okay, now I understand. So what you get is what? So from here you get the plus 1. Sorry. So another computation you need to do is b minus 1, b1, b minus 1, and then so you need to plug this one into here. So then C1, B minus 1, 1. I think that's what we need to do into here. And this, do you understand what I mean? So I just plug, so this state into here, and see what's going to happen in the relevant time. And also another piece we need to be careful is that this is something like a C minus 1, and then you just plug this one into here. So B1 C minus 1, and then C1. But I think we need to be careful both. I think even here, when you sandwich here, we need to plug this one and also this one. So B1 and B minus 1 should anti-commute. So therefore, oh sorry, so then maybe I should be careful about here, even here. So B minus 1, C1 minus C minus 1, B1, and B 0, and 0, B1, and C1, B minus 1, C1 minus C minus 1, B1. Okay, acts on here. So these are relevant part. Okay. And you have to do the anti-commutation relation, and also another piece is minus 2 here. Minus 2. Should be minus 2. Minus 2. So these are relevant part, and you should use the anti-commutation relation. I think this term is irrelevant because C minus 1, B minus 1 should anti-commute. And at the end of the day, B minus 1 hits it to here, so this is irrelevant. Okay, this is irrelevant. This is relevant. And also, I think we can do the same argument. C minus 1 and C1 anti-commute, and this B minus 1, C minus 1 anti-commute. At the end of the day, C minus 1 can hit on 0. So therefore, this is irrelevant. So what you need to be careful about C1 and the B1 commutation relation, I think, yeah. Okay, so if you do the honest computation like this way, at the end of the day, what you should get is indeed equal to k squared is equal to 1. K squared is equal to 0. So this is a condition you should get. Unfortunately, I cannot see now. I think we can do honest computation, then you get this one. Let's accept this one, let's move on. So when I have written down this lecture note, I should have done this computation. So I think I have done. I already forgot. It's 4 years ago. I have written that lecture note. And then, so let's do the other condition. So that the 0 is equal to QB psi. I will try to do this computation during the so 2k dot zeta c minus plus beta k dot alpha minus 1 k. So this is back here. And from here, one has to take k dot zeta equal to 0, and also beta has to be 0. Beta has to be 0. Okay, so therefore, so this is the condition that project. So this polarization vector. So this polarization, this is k, is the light vector. And the polarization vector has to be orthogonal to polarization vector. That's exactly the condition you need to obtain. The you need to impose. Okay. You need to impose from this condition. Okay. So this is the this is one condition, but here you still have 28 parameter, and you have 2 conditions. You need to have 2 more conditions to get the 24th state. So to get the 24 condition, one has to divide by QB exact term. For instance, if you have QB pi, so again it's the same computation. So this same computation will tell us that 2k dot zeta prime c minus 1 plus beta prime k dot alpha minus 1 k and this one. So this state can be understood unphysical. This is QB exact term. So this is QB exact term. So I just start with the state chi, such that it has a form like a whatever form. So you just put the prime, zeta prime dot alpha minus 1 plus beta prime e minus 1 plus gamma prime c minus 1 acts on vacuum. I just being lazy, just write on 0. And this QB acts on here. This is the Q exact term. Okay. So this is the so this means that the this part, if you can be written like this way, so this is the unphysical polarization. So therefore, sorry. I think I should look at this one. So therefore, if you compare this one and this one, so there's an ambiguity that you can just shift zeta to zeta prime plus beta k. Okay, so you can just shift zeta prime, so zeta to zeta plus beta k, because this is Q exact term, so this is unphysical polarization. Okay, if you compare with alpha minus 1, alpha minus coefficient alpha minus 1, so this is polarization vector for open string. And this is the polarization vector, unphysical polarization vector. So you can always shift this ambiguity. Okay. So this is beta prime. Sorry, this is beta prime. And also, if you look at the there should be a 2. 2. Okay. Thank you very much. 2. So if you look at the this c minus 1 part, okay, c minus 1 part, this is just number, okay. This number is just unphysical, okay. This number is unphysical. So zeta can be anything. zeta prime can be anything. So k contract zeta prime is some number. So this is unphysical. So therefore gamma is unphysical. Okay. So you kill this condition by BRSQ. Okay. And this beta is killed. And also this polarization vector also now, and this shift symmetry will tell us that the shift symmetry will tell us that 26 minus, at the end of the day, only physical degrees of freedom. Physical degrees of freedom. Okay. So that's the PRC quantization tell us. This part I didn't show clearly, but I hope you understand what's the meaning of PRC quantization from this analysis. Okay, let's take a break. So you have done the homework, just submit now. Oh yeah, and also I graded your homework, so if you submit the homework, please have patience, please patient. Please patient. Okay. Actually, not enough number of only 12, so you can only take one. Can you? No, you just apply QB on psi. So once you apply, QB is given. What's the QB expression? QB. QB is this one. So therefore, so once you act on, for instance, QB this time, I think, yeah. So n equal to -1 will see this one.
It only consider the first excited state in the Q.
No, QB is this expression. Just QB acts on psi, this one, and do the just honest computational relation.
And how's the K come from?
The K should come from alpha 0. So let's see. So how does it work? So what's L1? L1 should be part. You should be involved. Yeah. So now I understand. You should involve something like this one. Something like this one. So alpha 1 with anti-commute alpha -1, and you get some number, and the alpha 0 will give you. If you hit alpha 0 on K, you get the K. And then the rest of the term is -1. And then you get the -1. Do you understand?
And I also want to ask, so L is, yeah, this is from, and how can, I don't know how why the mode expansion is like this.
So from here. So sorry, L0?
Yeah, I mean L0. not how things
Because it's a bosonic mode. So I mean, T is equal to this one, right?
Yeah.
No, X mu. And minus 1 over alpha prime. I think something like this one. And this is equal to sum of Ln z minus n minus 2. And this can be written as some alpha blah blah blah.
and then compare.
Yeah.
There are many d equals to 26. Is there coincidence or
It's not coincidence.
have deeper mathematics?
Huh?
Have deeper reason?
Of course. The target space has to be d equals 26. Inner for string theory to make sense. Bosonic string.
And another question is, in here he has 28 parameters and have two constraints. Why 28 minus 2 plus 6 and
So I told you. So you need to get rid of the exact term. Therefore, so gamma. So cubic exact term distance is unphysical. So the gamma is unphysical. And also there is shift symmetry for polarization vector. That will kill two conditions. Another two conditions. So not all students, unfortunately, only 12. So you can take first come, first served basis. I think these are irrelevant one. These are irrelevant. Only this one we cancel as 2, I think. How do you get it?
Can I submit my homework on WeChat? Because I can't submit on the e-learning.
What?
I can submit homework on e-learning because I'm participating.
What?
I can submit the homework on the e-learning, so can I submit the homework via
Can
WeChat?
what? Can submit a homework what?
Via WeChat.
That's fine. If it is PDF, it's okay.
It's PDF.
So you can have one shipwreck if you want. There's still like 8 left, but not 2.
Where does this come from?
Just plug this one into here.
And the size, this one?
Just compute the coincidence. So this is something like that. So what's relevant is here it's only like the alpha 1 anti-commit space. Okay. That's a therefore. And then as far as I'm a C0, that's unphysical, right?
Yeah.
So therefore, if you have 1, 1, C0, so C0 is unphysical. So you can forget about it. Alpha 1 and alpha 0 and C minus 1. This is the relevant part. The rest of the part, for instance, if you consider C1, you have alpha 1, alpha minus 2. But sorry, C1 annihilates this vacuum. So it's irrelevant. Sorry. So if you consider minus 2, this becomes minus 1? No, sorry. This is 1, right? This should be 2, so it should be plus, right? But if you have 2 of them plus sign, annihilates the vacuum. So what's relevant over this one? So therefore, alpha 1 and alpha minus 1 are they commutes, right? Commute, right? And get the plus 1 or something. And the alpha 0 will get the k, right? Actually. And the c minus 1 remains. So therefore, you get the c minus 1 and the k. Likewise, you can do the same exercise for beta here. And gamma here is analysis. So you can do the same exercise for just including this one. I think what oh, I see. So now I understand what's going on. So this part is irrelevant, I think. Only this part is relevant part. And then to get this one, I think we will use C1 and E minus 1 on the contemporation. Plus minus 1. So then C1 is relevant, right? So I think what's relevant is C1 alpha not alpha minus 1 is relevant. Therefore, alpha minus 1 left, and C1 anti-commits to E minus 1, and it's gives us a number. The alpha 0 will get the k. Then that's it. And the rest of the part just annihilates everything. So you can pick one. Seems like nobody willing to. Okay. There's no poison inside, don't worry. I see.
对呀，这个解决讲外，这是比赛，这个如何喜欢的，是的，我之前是也错，但是按道理来讲，就是我也是按道理应该可以调整，是按二数来，就单位统一，它就是有这个道理，就是正常做法都是这么开始，没告诉我，正常做法都是别人，没告诉就错时候那种对接。 那肯定是有点化学的问题，就是可是我拿做。
Okay, so let's get started. Unfortunately, during the break, I don't know how. I couldn't remind myself that how you obtain k² equal to 0. So I think it's good exercise. You should be able to obtain this k² equal to 0 condition if you do honest computation. Yeah, so I think after the lecture I will try to check by myself too, but you can also try to derive this condition. But anyway, so this condition is almost obvious because it's first excited states. And what's important, this part. Now this is just direct computation, physically. Okay, so let's talk about the amplitude. So as I mentioned, so last time I briefly give you what is the modular space or Riemann surface. So as I mentioned last time, so there is a ambiguity for the metric So metric, but if you do the component transformation, so if you do the component transformation, that cancels with Weyl symmetry. Okay, so essentially it doesn't change the metric. So therefore, there is some still redundancy even though we did gauge fixing. So there's a modular appears, and last time I just told you a bit lie. So even a Riemann surface, so you have parts decomposition. So this line, the normal line is indeed equal to 3g minus 3, orange line. So this is Riemann surface 4, genus 4. So it should be 12 minus 3 is 9. 1, 2, 3, 4, 5, 6, 7, 9, right? So then you get the parts decomposition. So in tachymetric space, last time I just told you like 6g minus 6, but this is not true. So last time I told you 6g minus 6, but this is not true. Indeed, you have 3g minus 3 times r plus 3g minus 3. So this is tachymetric space indeed. So unfortunately, I didn't have time to edit. I'm crazily busy to this and that. So I didn't have time to edit section 6, but next week I will make a significant revision in section 6. So bear with this poor note, including this kind of stuff. So it's called Pensionism coordinate. Pensionism coordinate. So, I mean, one can introduce some unique hyperbolic metric on the Riemann surface genus greater than 1. And then these pans has some lengths in terms of the hyperbolic metric. And also, so you can have some geodesic in terms of metric. So in the differential geometry course, so I introduce so-called the Poincare disk. Poincare disk. And then one can just have take geodesic to have genus greater than one Riemann surface by just cutting along and gluing B inverse B inverse B inverse C C inverse D inverse, and what you end up with the Riemann 2 CD D C inverse D inverse, and what you end up with the genus 2 Riemann surface with the so A, B, C, D. So the Riemann surface has the unique hyperbolic structure, and if you do the Pont's decomposition, one can have the geodesic in terms of this hyperbolic metric, and then they intersect with orthogonally. So, okay. And then, so when you glue the pants, so when you glue pants, how to say, pants by identify edges, so there's a, how to say, way to specify the angle. So angle, so one can just specify how to glue. That's actually Pensionism called an angle shader. So when you glue them, this edge to another edge, there's a you need to specify how to glue the angle. So this length of the edge and shader is called Pensionism coordinate. So that will determine the shape of this Riemann surface. Essential. But so this is Taylor space. So this R plus is the coordinate for L, theta for coordinate for R is coordinate for theta, and there is 3g minus 3 way to cut the long Riemann surface. But however, so as I mentioned last time, so there is a so-called ambiguity by Dan twist. And the last time I just mixed up the Pont's decomposition and Dan twist. And Dan twist actually can be done by 3g minus 1 along this curve. I already forgot how to. So let's see. So 3g minus 1. So when genus g equal to 4, 20, so it should be 11, right? So one is this one, one is this one, one is this one, and one is this one. Then another is the here, 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 and then another color I need maybe yellow. So now 4, 3, 7, and another color is this one. Unfortunately, still, oh yeah, one more. So my hand drawing is horrible. Sorry, it's too much. So there's a 3g minus 3, the one cycle, or one-dimensional curve, one can take 3g minus 1, sorry, 3g minus 1 curve, one can take like this way. 1, 2, 3, 4. 8 plus 3 is 11. Okay, good. So this is the cycle you can do the Dan twist. So once you glue the along this blue line, there is a symmetry that goes to theta plus 2 pi. That will create so-called mapping cross group. Mapping cross group action, so that the in the case of torus, it's easy to see. So in the case of torus, genus equal to 1. Okay, genus equal to 1, so that the two generator for mapping cross groups, that is equal to T and S. I told you last time. Okay, T and S transformation last time. For genus high genus, you have a 3G minus 1 generator that generates so-called big robust transformation, gauge transformation, or just discrete group, so that the modular space for Riemann surface Mg is equal to type mirror G divided by mapping cross group. Okay. So as you can easily see, this is the 6G minus 6 dimension, real dimension. And if you add a puncture, so this puncture can move around this Riemann surface. So one puncture can have a moduli for 2n degrees. It's real two-dimensional, so you can just move around two-dimensional surface. So therefore, each puncture will give you 2 moduli. Okay. Therefore, if dimension of real dimension of modular space of n puncture from genus G Riemann surface is 6G minus 6 plus 2 times n. Okay. So that's the dimension for modular space of Riemann surface, puncture Riemann surface. So this degrees of freedom is actually some needs to be included to compute this string amplitude, as I mentioned last time briefly. Okay. Oh my goodness. Today, I'm sorry, it's a bit slow because last week I was too rush, and also I didn't have time to prepare lecture so much. Okay, so let's do step by step. What was the choke? Okay, so as I mentioned, the conformal killing vector. So the variation of symmetric over there, infinitesimal version, is given by here. As I mentioned, 2p dot v ab plus 2 omega tilde HAB. And the conformal killing vector is a solution that namely omega tilde such that the conformal killing vector is equal to 0. So then the epsilon is called conformal killing vector. Okay, on the other hand, let's see. So there is a so-called the changing of metric. So this is the conformal transformation. There is another transformation one can consider, which is the I call it HAB, perpendicular. Okay. So perpendicular, so that is the moduli for metric. So then this one is can be understood as that is orthogonal to this transformation. So here you can have it doesn't change it's just Weyl symmetry and also diffeomorphism. And then so here you can just explicitly change the metric. Okay, this is explicitly. It's not the symmetry of the path integral, but that is orthogonal to this direction. So to see that, we just look at the orthogonal. Just impose this orthogonality condition, and then do the integral over the Riemann surface d squared square root h, d squared sigma square root h. Okay, so then do that. So here it's just the inner product. H is HAB and HAB. Or in the note, I take the opposite way. So they are orthogonal. So this is intrinsically changed the worship metric. And then do the integral by parts. So this is just a differential operator. So I just do the integral by parts. So this can be written in as follows: d squared sigma, and then p delta th. And this is p. This is adjoint operator. So you just do the integral by parts. It acts on here. So that's an adjoint operator or trace. They also want the perpendicular A plus 2 omega tilde HAB delta transpose HAB. So to satisfy this equation for arbitrary E and then arbitrary for any E and omega tilde, this condition has to be satisfied, which means the orthogonal direction is really need to satisfy this condition. And then HAB and delta T HAB equals to 0. And taking so plug explicit expression to this T, what you end up with. So since just plug expressions of P into here, so what you end up with nabla A delta T HAB plus nabla B delta HAB and plus I already forgot the minus H delta T HAB times HAB yeah, and take derivative, okay, equal to 0. And since this is always 0, so you can ignore this term. And then since HAB is always symmetric, so this equation boils down to delta HAB equal to 0. So this is the equation for the change of metric that is really that change. So what I meant is so this is HAB, space of HAB, and then there is a gauge transformation that is generated by Weyl and diffeomorphism. And we can take a slice by fixing gauge, okay? Fixing gauge. And this delta perpendicular HAB is the direction that goes to this direction, okay? Instead of so this direction is the really, oh, so sorry. I completely told you wrong. This direction, sorry. My brain is not. So the gauge transformation, this is gauge transformation, okay? This is gauge transformation. Therefore, this is gauge direction. A perpendicular is gauge direction. I mean, it's hard to, my drawing's not compatible with this one, but so this is gauge orbit and it's perpendicular. HAB is perpendicular. Is that what you mean? Should satisfy this condition, okay? If you take the conformal gauge, so if you take ds curve is equal to e to the omega d whatever dz bar. So this is to take conformal gauge. So conformal Killing vector equation is just to become this one's already did many times. So this is the conformal Killing vector equation. And for metric orthogonal, so if you use the conformal gauge, this becomes just an ordinary derivative. Holomorphic anti-holomorphic derivative. Okay, this is metric moduli. Okay, so let's start looking at the example. So how does so in the case of sphere, I think I told you totally wrong thing. Sorry. Oh my goodness, so sorry. Yeah, I think I told you completely wrong thing. This is not correct. This is not correct. Sorry. Let me think why I made a mistake. No, I think it's okay. Is it okay? Yeah, I think. I'm sorry. So what I explained is okay. Sorry. It's okay. It was okay. Sorry. It was okay. So this is gauge orbit, and then fix the gauge, and this direction is generated by this one. This direction is generated by perpendicular. Sorry, it's okay. So let's look at sphere S2. If the worldsheet is S2. So S2, as you know, so there's a sphere S2, okay, and then there's stereographic projection. So S2 can be understood as the so S2 can be understood C is infinity, or S2 can be understood, or south pole, and these can be understood as north pole by using stereographic projection. So you just have to put the north pole and get rid of it, and just take the one-to-one corresponding sphere, the point, and that intersect with the plane on that intersect with the in the gray circle equator. Okay, that's straight projection, and one coordinate is just S2 divided by mod S2 mod north pole will give you this local open chart, and another chart you just get rid of south pole to get another chart, and you just identify. Okay, that's you have a coordinate transformation in between. So if you call this one Z plane and W plane, if they are related by the coordinate transformation, just related by W is equal to 1 over Z. So that's very intuitively clear. So that the so for instance, if you take this point, it intersects here, so and the south pole take here, you get the around here. So that everything, how to say, outside of the circle, it becomes inside. Due to this 1 over Z identification. So therefore, this coordinate transformation will tell us that if you do the delta W is equal to partial. So if you take the infinitesimal transformation for this coordinate transformation, you get the -2 delta Z. And also under this transformation, the metric infinitesimal metric change is given by delta ZZ. Okay, so this is the coordinate transformation on the dispatch. It translates into the coordinate transformation dispatch up to this factor. If you change the metric on the dispatch, will be seen delta HZZ. The metric transformation on dispatch, okay, up to this factor, okay. And in order for them to satisfy this condition, for this condition in conformal gauge, so it has to be holomorphic everywhere. So this conformal killing vector will tell us that everything has to be holomorphic. This epsilon has to be holomorphic. Okay, the conformal transformation has to be holomorphic. Okay, for everywhere. But as I mentioned, the conformal transformation in the dispatch is related to conformal transformation dispatch by up to this factor. In order for to be holomorphic everywhere, this -2 has to cancel, so that the epsilon can only take the following form. Okay, if you take this form and go to here, what you would see is that if you do that, if you write down everything in terms of W, it becomes a 1 over W. Okay. But up to this transformation factor, so you get a -2 minus Z square means minus W square, right? W square. Okay, so therefore plus a 2W square. Oh, sorry. Okay, on this patch. So therefore W square and W square will cancel. There's no singularity here. It's holomorphic everywhere in this CW. Okay, CW patch. So therefore, if you have one more, like a Z cube, 3. Okay, then what you end up with, you have a 3W cube. Okay, this is not well defined on the south pole. Okay, south pole in the origin of this one. Okay, do you understand? So therefore, you cannot include as a conformal transformation for sphere, conformal killing vector. So conformal killing vector only have 3 moduli, but you cannot include this one. In similar way, so to define, so here HCV has to be holomorphic. Okay. However, the same reasoning will tell you that this is, you have Z to the fourth term. Okay, Z to the fourth term. So therefore, there is no way to have this holomorphic change of the metric all over the sphere. Okay, so therefore, there is no metric moduli. So in sphere, I have a so holomorphic, anti-holomorphic part. Holomorphic will give you 3 complex scaling vector field. Anti-holomorphic part is 3 complex scaling vector, but no metric moduli. So let's look at the torus case. Torus case is just flat. So but you need to identify, so flat, but you need to identify, okay, holomorphic function which is well defined on this identification, okay, identification. So therefore, so this one is only constant one is allowed, okay. If you have a varied by Z, you cannot identify in the top and bottom and then left and right. If you depends on the coordinate, you cannot identify. So if you consider torus T2 is C2 C mod the discrete group Z. Okay. If Z is the coordinate of C, you cannot identify top and bottom, left and right. Okay. So therefore, it's only the constant part is this is one component killing vector. And the metric also can have the constant term. One metric moduli. For holomorphic part and also anti-holomorphic part. Oh, I didn't include anti-holomorphic part. I mean, sorry. So in total 2 and 2. So for torus. So in relation to so in fact this compound killing vector and also the metric modulites are related to BC ghost, equation motion of BC ghost. If you consider ghost is equal to 1 over 2 pi square root h d square z BAB. So this was the action for the ghost. This was the action for ghost. And then so equation motion can be understood as the P dot C is equal to delta A CB plus delta B CA minus HAB that's equal to 0, and also delta A BAB equal to 0. Essentially, this one really coming from original action. Original action used to be the same factor divided by square root h d yeah, this square sigma, I should call sigma. And then what we have done is BAB and then P dot C, right? And then AB. So this is the original action we take, okay? So this is the original equation motion. So this is exactly the conformal vector, and this is the equation motion for metric moduli. And genus equal to, so genus G with 0, 1, 2, or genus G. So then what we saw is the number of the zero mode, C and B, is indeed, so this Z, so the mode that satisfies this condition is called zero mode. For this condition, for C is indeed, so this is 2, 2. So that's very easy. So you have a 2 conformal killing the 2 metric moduli. Whereas in S2 case, you have 6 conformal killing vector, but no metric moduli. And then, so the situation becomes opposite when you greater than, when the genus is greater than 1, 6G minus 6. Okay, so if once you take the difference between them, you have minus 6, 0, 6G minus 6. Okay. So this is indeed encodes the dimension of the MG. Understand? So the difference between a conformal Killen vector and the metric moduli is indeed encodes the dimension of the modular space of Riemann surface. So that's what it means. So the yeah, I mean 6G. Sorry, I mean. I think told you wrong. So sorry. How can I explain to you? So I think I'm doing project. Next time I will explain a bit more detail. So this one is dimension of R, metric modular dimension R of modular space of Riemann surface. Whereas this one is dimension of conformal Killing vector, dimension of the conformal Killing vector. So that's the meaning of metric modular is really the modular space of Riemann surface. And for instance, and difference between them will give you some Euler characteristic. Times 3, minus 3. So the reason why we are doing this kind of stuff is that to compute the amplitude, you need to somehow incorporate the ghost mode. So once you incorporate, once you try to compute some b hat k, so you cannot compute the string amplitude directly. So one has to include so-called BC ghost in here to have the non-zero amplitude. You need to insert ghost mode, and then integrate out the modular space of Riemann surface. Integrate the moduli for Riemann surface. That's what we need to do. And to see what kind of BC ghost you need to include is that you need to take a look at the ghost anomaly. Unfortunately, I don't think I have time to talk about within the 5 minutes. So once you incorporate ghost anomaly number, what you end up with, you have to include, you need to include C, number of C has minus number of B has to be, 3G minus 3. 3G minus 3. So insertion for the BC ghost insertion has to obey this condition in order for the ghost anomaly is absent. And the similar thing will happen C bar minus number of B bar is 3G minus 3. In total, you will get the other one. Sorry. Minus. You have to include this kind of number. This number. So this conclusion can be obtained from absence of ghost anomaly. So that So that's what we are going to see from the. Again, we will look at the conservation of the current for ghost current is proportional to kappa times R2. That is related to curved worldsheet, which is scalar. And from here, we will see the consequence of this ghost anomaly for the string aperture. Yeah, I don't think I can explain in detail within a few minutes, so let's stop here today, and I will explain a bit more detail in next lecture. Okay. Since I didn't go into the detail of the amplitude today, so the homework 5 should be postponed to next week. So there is no homework this week.
I think I was wrong about this. It has nothing to do with any computation of B1, C minus 1.
What?
I think this is just a normal ordering, right? So 1 moves
Oh, yeah.
There should be a trailing minus 1 here.
Okay.
So I think what's wrong is this equation.
Okay.
So there shouldn't be minus 2 here.
There shouldn't be. Okay.
Because this one would give you, this alpha prime p squared would give you alpha prime k squared cosine, right?
Okay.
And so this 3 would give you another cosine. And this trailing minus 1 would give you that minus 1 cosine.
Can you write it? Sorry. Can you write?
So if you have this, so and minus 1. So this one would give you alpha prime k squared cosine, right? Because p squared commutes with all this. For
This one. Yeah.
You only get this one.
Yeah.
And this, so this 3 combined give you another cosine.
Okay.
And this minus 1 gives you another.
Okay. Sorry, these three will give you difference?
Yes.
Okay.
Because alpha 1 commutes with B and C, and it annihilates this thing.
Yeah.
So alpha 1, alpha minus 1 will give you 1 plus alpha 1.
Yeah, that I understand. But how about this one?
The other,
用到了消掉。如果用到了发射 B 的人，
so this is the same because C1 has nothing to do with alpha else.
Okay.
Right. And only this B minus 1.
Yeah.
So the
用到了是
anti-conjugate
他是发射 B 的人，他是
Without n plus n, right?
对，你要这个类型的
Yeah,
话，就
that's true.
so,
你是有
so this would give
这
you
这个肯定不是，这是一个没了，
Okay.
这个是，这玩意儿这个
Okay.
oh, but what about the minus side?
这个可能是这样的吧，这个其实我讲过那个
I would imagine if you cancel and
反正不可能它这里，
cancel this one, that's what's going to happen.
所以这个减下一下刚好是，你这有这里有两项，刚好是三项，
老是怀疑用到
应该是变成这个 plus 2 no minus 2.
B 发射八次，发射 B 发射。
I can see. Yeah, I would check.
What is the P means? Is there any meanings? The P of that? Or is just a definition? So the PT the PT, what is PT mean?
Just adjoint operator.
Oh.
By integral by parts.
这个是算上
Sorry, how? So it should be minus 1.
好像是。这三种基础，它是就上标词和比手啊，多一个这个意识数。就是这个，它是A B 是这个。
How do you divide this? From here, how do you divide this? How do you divide between actions?
就像水土。
I think I'm looking at the modification here.
相对比没有发射，这个它是只有判断方向对。
算了。
这是刚好是3就应该
没有发射 B 的意思。足够判断 B 那条线。每个地方都它力量放。就是它自己。
I think I gradually understand why that minus 1 minus 2 标识。Yeah. I think I just open this. Look at this. And then I just. What's the one? So I need to make this. Oh, I need to stop the recording.